All right, so I've pushed a couple of notebooks to my repository. We've got 0301 and 0302. I expect to get through all of 0301 today, and if I go through it too quickly, we could start 0302. But the plan is 0301 for today. And so, as always, you can do a git fetch and a git merge to get your version copy in, and then again, I recommend that you make a duplicate of it for you to work on, so that when you commit your changes and I commit my changes, we won't run into a merge conflict. Okay, so NumPy should come installed when you set up Anaconda. Okay, and so what NumPy is it's I guess it's a module or package or something, whatever we call these things in Python, that basically create NumPy arrays, which behave like atomic vectors in R. Okay, and so in order to do that, in order to get that functionality, the first thing you need to do is you need to import NumPy into pandas. And you can just type in import NumPy and it will, into Python. You can just type in import NumPy and it will work. Okay. The general convention is to do import NumPy as NP. Okay. And this is technically this part that comes after as. You could put in any name that you want. If you want to call it num or whatever, you can. It's just that people will have a hard time reading your code. This is kind of the convention that everybody uses, so that later on, when you call a command and you see np.array, this is the signal to everybody that you are using NumPy. So this is just kind of the convention. There's no rule in the pandas language that it has to be NP. But this is just what everybody does, okay? And it usually takes a couple of seconds to load, especially if it's the very first time you're doing it. And then you can see what version of NumPy you have, which is np.__version__. I actually have my version's a little bit old, I think. I think we're at like NumPy 1.17 or something. What do you guys have? Okay, anyway, to update, you can always go to your terminal and type in conda update NumPy or conda update all. What do you have?
1.13.
1.13, okay. So, you know, the recommendation is you should always keep your software up to date. But mine's you know, I was running into trouble when I tried to update my packages, so that's why I haven't updated them yet. But that's what we have. Okay, so so the key thing with a NumPy array is that all the values in the NumPy array have to be of the same data type. Okay, so in lists you don't have that requirement. You can have strings and integers and floats and booleans all mixed in there in a list. Okay, even other lists, right? With an array, NumPy array, everything in the array has to be of the same data type. Okay, so here to create a NumPy array, you use the function numpy.array parentheses. Okay, and again, so anytime you see NP, that means NumPy. Okay, so you call numpy.array, and so here I'm putting in a list with the integers 1, 2, 3, and I'm calling NumPy array. And so this creates an array. I haven't assigned it anywhere, so it's just going to return that value, the result here. Okay. So when I do this, it comes back and it spits out array, and then square bracket 1, 2, 3. Here I'm going to assign the same array to the name A, and then I'll ask Python to print out what A looks like, okay? And this is what it looks like, okay? So we've got square bracket 1, 2, 3. All right, so this looks different from here. Okay, and maybe I'll just add a printed list has commas. Those are commas. Okay, so if I just print a list with the values 1, 2, 3, it includes the commas. So when you are looking at stuff in Python, you can distinguish between a Numpy array and a Python list with values of integers, because this does not have commas between them, whereas the list does. Okay, and if I ask what is this type here, it's going to tell me that it's a Numpy ND array. Okay. If you give it a list with mixed data types and you say make an array out of this, Numpy will what we call upcast. It's the same idea as coercing. It's going to upcast all of the data values into the kind of the least restrictive data type, right? So in this case, we've got integers, floats, and booleans, and it's going to upcast all of these into floats, because that's the least restrictive data type. Okay, so we're going to get 1.0, 2.0, 3.0. False will be 0.0, and true will be 0.0. I mean 1.0. Okay, or maybe it'll just be 1.2.3. Okay, yeah, that's what we get. Okay, 1.2.3.0 and 1 point. Okay, and we can tell that they are floats because they have the decimal value. There's no commas there. That's going to be how we distinguish between a Python list and a Numpy array when we print. Okay, here I've got 3 in quotes, so everything is going to get upcast to strings. Okay, and so there you go. So that's expected, right? Okay. The way you create a matrix or a multi-dimensional array is you can provide it a list of lists. So here I'm saying make an array out of, and you can see I've got the first list. So it's a list, and in that list are 2 lists of length 3 each. Okay, so I've got a list 1, 2, 3, and then another list 4, 5, 6. And I say make an array out of this, and when you print it, it looks like this. Okay, this is the way a matrix. Okay, this is just a 2-dimensional Numpy array, an ND array, n-dimensional array, and this is what it looks like. Okay, so this is basically a 2x3 matrix, and you can tell that it's that there's 2 dimensions here is because the opening square bracket is that there's 2 square brackets here. Okay, there's 2 square brackets to open, which means we've got 2 dimensions. One for the number of rows and one for the number of columns. You can make higher dimensional arrays as well, and you'll have that many square brackets as well. All right. If you give it a list of lists, but the lists don't align in length, okay, so here I've got list 1, 2, 3, and another list with elements 4, 5. So those don't align. You're going to get an array of lists, which is not as useful. So here it says a list with 1, 2, 3, and a list of 4, 5, which is probably not what we want. Okay. All right. You might make arrays manually by kind of typing in your values, okay? But most likely you're going to use probably either one of these functions or the range or the linspace. So these are other quick ways to make arrays. All right. So if you just want to make an array of zeros, all right, you're going to type in numpy zeros, and this says I want an array with 5 0 values here, okay? And because I didn't call print, it actually returns the object, okay? So notice every time you call print, there's no output, okay? There's no value that's returned. The returned value is none, so there's no output. but it's printing the array to the screen. Here it's returning this, and I can use this for something else. Okay, so NumPy zeros will make float type zeros. Okay, if you want integers, you can specify data type d type to be ints. Okay, and you can do zeros as well. Whoops. All right, and so there we get integer type zeros. You can give it, instead of just a single number, you can give it a list or a tuple with dimensions. Okay, and so this will create a two-dimensional array, okay, or a matrix with 2 rows and 4 columns. So there we go, and this will create a 3-dimensional array. Okay, so here it will have 2 sheets, each with 3 rows and 4 columns here. Okay, and again, when you look at this, you can tell that it's a 3-dimensional array because there's 3 opening square brackets. Okay, 3 opening square brackets, and this is kind of like the end of like one 2-dimensional thing, and then there we go. Okay, and then there's no upper limit, I don't think, on how many dimensions an array can have. Okay, so here's a 4-dimensional thing, which is a lot. Okay, so here's your first kind of, I've got 2 blocks. Each block has 3 sheets or 3 layers, and each of those layers has 4 rows and 5 columns. So I don't. Okay, so just imagine one kind of block here and another block, and now you've got a 5-dimensional array. Or I'm sorry, 4-dimensional array. Okay, you've got np.ones, same thing as zeros, except it puts in ones instead of 0. Okay, so that's an option. All right, and then you also have np.full, numpy full, and that lets you pick an arbitrary value that just gets repeated. So this will create what, a 2x3 matrix or 2x3 array with the value 1.2 inserted everywhere. Okay. I think zeros is probably, you'll see that frequently when reading other people's code. Okay, you can do random numbers as well, all right? Like R and like pretty much all modern programs, with the exception of like Excel, it uses the Mersenne twister, okay? Jake, did you ever read about the Mersenne twister, how it works?
Not in depth.
No, yeah. I don't understand how it works. It does some bit shifting stuff. It's complex, but everybody uses it, and we're just like, okay, it works. So so that's what we've got. So you can specify a seed, okay? Other functions to specify the random seed, there's another function I think called random.state, and I honestly don't know the difference between, let me see, Numpy Random. So, okay, yeah, anytime you want to look up documentation, you just type in NumPy whatever, okay? All right, so we've got random sampling, numpy.random, and let's see. So you can specify random state and seed, or you can ask get the state or set the state. So I'm not 100% sure the difference between these. Let's see. So random seed the generator, okay, and random state. Okay, it does something, but I don't know. Okay. All right, but anyway, so here I'm going to just set the seed to 1. You can get random numbers, okay? Random uniform is random.random, okay? np.random.random, and that's random uniform values. Random normal is random.randn. Okay, so numpy.random.randn, and this will give you 5 values from the random normal distribution. Here you can say, I want random.normal. Okay, so random normal will give you from the randn will do standard normal, but here you can also specify I want have a mean 10, standard deviation 3, and I want 8 values arranged in a 2x4 matrix. Okay, and that will also work. Okay, so mean 10, standard deviation 3, things like that. Random integers, 0 from 0 to 10. Okay, 0 inclusive and 10 exclusive. So much like using kind of the same notation as the range, where it basically goes from 0 to 9, okay? 0, 10, 20. So this says 0 inclusive, 10 exclusive, return 20 values here. And that will give you 20 random integers or random digits, okay? If you wanted to simulate, say, die rolls, you can do randint 17 50, okay? And that will be 50 dice rolls. Okay. And then, you know, as always, you can go to, you can type in Numpy Random and into Google, and you've got a whole bunch of other things, okay? So kind of the simple random will probably be the ones you use the most, but you can as well generate from a bunch of different probability distributions, right? So you're doing Monte Carlo methods. You can generate from the beta, binomial, chi-squared, Dirichlet, exponential, F, gamma, geometric, Gumbel. What's Gumbel? Okay, it's e to the x, I think, right? I don't know. What's here? Non-central chi-square. Do we know what that is? When do we use the non-central? Okay, but anyway, all of these things. The von Mises distribution. I'm gonna have to look that up because I don't remember that one. All right. Well, anyway, all of these things, they're there, so you can use it. Okay. This is probably what we like. Okay. So if you remember range from regular old base Python, okay. So this is what will the next thing do, right? So I've got range 0, 10, 2, and if I throw that into a list, what will I get? 0, 2, 4, 6, 8. Do I get 10 or no? No 10, right? 10 is not included. So 0 through 8 by 2, okay? In NumPy, same thing, okay? It's NumPy A range for array. Make an array out of this range. And it uses the same styling as the range object in Python, okay? So you just say np A range 0, 10, 2, and we get this, but it's a NumPy array, okay? All right, you could create the range object in Python and then throw it into numpy.array. There's no rule against that, okay? I mean, if you did this, this one's going to be faster. Numpy.arange will be faster. All right, and here's Numpy arange 0, 105. So that starts at 0, ends at 95, step size 5. Okay, and then probably the quickest, arange 20 will go what? 0 through 19. Okay, yes, question?
So what is that about the range object? How is it different from the array or?
So range is in base Python, and it does not require NumPy. Okay, once you have NumPy, you can use arange, numpy.arange.
So what's the benefit of using arange rather than range?
Well, it creates a NumPy array, and NumPy arrays all have to be of the same type. So technically, you could create a range, turn it into a list, and then modify the third thing to a string. Okay, That's not going to happen with Python and with NumPy. You change the third thing to a string, it's going to upcast the entire array to a string, okay? Because NumPy enforces that all the array elements are of the same type, data type, to keep things faster, right? So technically in memory, and we don't really care because all of our computers have what, 4 gigabytes, 8 gigabytes. Our phone has 4 gigabytes of RAM, okay? We're not running into major performance issues for our small little projects right now, okay? Maybe on larger scale things you need to talk to someone who's into optimization for memory and stuff. But technically, list operations in Python are a lot smaller because there's a lot more overhead because it has to keep track of the data type of every element in the list, whereas for a NumPy array, it does not. It just says this NumPy array is of this data type and everything in here is of the same data type. So NumPy arrays, so A range will generally give you better performance if you're working with a range type object. Okay, you can create something called linspace. Okay, linearly spaced values, and so this will say I want to start 0 and end at 100. Okay, inclusive, and I want them evenly spaced, and I want 11 values. So the first thing will be 0. And if we want 11, it's going to go 0, 10, 20, 30, 40, 50, 60, 80, 90, 100, right? Because with linspace, different from range, okay, you are giving it a start and a stop, and the stop is included, and you're telling how many you want, right? If I do linspace 0, 110, then they're spaced out 11.11 each. Okay. You have the option to do endpoint equals false, and then it will space everything out, but it won't include the 100 here. All right. And so this will go 0 through 90. All right. And here, if I do 0, 109, endpoint false, then it ends at 88.89, okay? And so this endpoint equals false kind of messes with their heads a little bit because, you know, it's like the calculations are done for 0, 110, and then we just drop the last number, okay? It's not that, right? Because if you had to figure out how did we pick 88.89 as the endpoint for this one, it was that we basically did 0, 100, okay? The difference between here is 100 values. We divide that by 9, okay? And then we end up like this, okay? Whereas over here, I think if you're expecting to include the end space, I think it makes a little bit more sense. But I don't know. That's just how linspace works, okay? This is it's handy. Okay. All right. Let's talk about the array attributes themselves, okay? So here, I'm going to create an array of 1s, 3 by 4, right? And so this is what it looks like, okay? Each array has these attributes. ndim is the number of dimensions. So how many dimensions do I have here? X.ndim will return 2, right? I've got rows and columns. So I've got two dimensions. The shape will be a tuple with the size of each dimension, okay? So it's going to say you've got 3 rows and 4 columns. So you're going to get a tuple that says 3, 4, okay? And then the D type is what type of values. So this will tell me what? So this, what kind of values are in here? Do I have ints, floats, strings? Floats, right? Because we got the little dots behind the ones. Okay? And it tells me indeed, float. Float 64, mean 64 bits for each floating number, right? So 8 bytes, so that's your double precision float. Okay? So here I'm creating an A range object, 0, 12, 1. Okay, and this is what it looks like. All right, how many dimensions do I have? So Y has how many dimensions? Just one dimension, right? It's a one-dimensional array, okay? And so the shape is going to, and this is a little strange, okay? The shape is a tuple with just one element in there, okay? It's a one-dimensional array. There's no second dimension here. Okay, it's not a 1 by 12 row matrix. It's a one-dimensional array. All right. All right. You can reshape arrays on the fly using NumPy's reshape. Okay. So here again, I've created J. J is a one-dimensional array, 12 elements, 0 through 11, and I can reshape this. I can say reshape J into a 3 by 4 array, and this will produce K. Okay, and so K is 3 by 4 here. This command reshape does not affect the original J. This will create a copy. So this method leaves J unaffected. Right. So these are just you just kind of have to remember the behavior of each of these things. Does it modify in place or not? So you have that. Okay. One thing to note is that when you reshape an array in Python, the ordering of the values is different from R. So in R, you could do something similar. You could assign dimensions to a vector after the fact, but the way it fills out that matrix is it goes down the columns, okay? And in Python, it goes across the rows first. So if you're expecting the same behavior, you know, it's not exactly the same. It's a different language. It's got its own conventions about these things. All right, so here if I take J and I reshape it to 4 by 3, we're gonna go 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, 11. So 4 rows, 3 columns. Again, J remains unchanged. Here is K. K is the 3 by 4. And you can do K dot T. K dot T is the transpose of K. All right. So the dot T is actually an attribute of this this matrix K, or NumPy array K. Right. So K dot T is this transpose, right? And so that's what we expect. Yeah.
When you say it's an attribute, does that mean that it's always stored and it doesn't create it on the fly when it's requested?
I think it's created on the fly. I don't know, actually. I think it's something inherent to the array object, but I don't know internally if it's made on the fly or not. But yeah, okay. I think it's just inherent to the object is that it has this transpose thing. Okay, so we've got K and we have the transpose K dot T. All right, and again, K is not affected here, right? So you can take the methods and you can kind of chain them as well. Okay, so here I'm doing NP dot arrange, okay, I'm sorry, a range, all right, so this creates a length 12 matrix, or I'm sorry, a length 12 one-dimensional array, and then I can reshape this, and then I can then call transpose on that, okay, and so you can kind of chain these things using this dot notation, and what will this produce? what will the dimensions, how many rows will it be? 4 rows, 3 columns, and the first column will go 0, 1, 2, 3. Yeah? All right. Here's one thing to note, okay? So with y.shape, y is this one-dimensional array. The shape here is that there are 12 elements in it, okay? And there's no second dimension. So here, if I say transpose this, okay? So this is what y looks like. If I transpose it, it looks exactly the same, okay? If I ask what is the shape of this thing transpose, oops, it's also 12 comma, okay? Because it's one dimension. So you can't, there's no dimensions to actually transpose, right? So it just leaves it like that, right? Now I could take y and I can reshape it to be a two-dimensional array with 1 row and 12 columns, okay? And the only way we can tell the difference between y.transpose and z, or y, which is a one-dimensional array with 12 elements, and z, which is a 1 by 12 array, okay, 1 row, 12, is that this has the double square brackets, right? The opening, there's 2 square brackets, and here there's 1. So by seeing that there's 2 square brackets, we know that this is a two-dimensional array, 1 row, 12 columns. Whereas here, there's only 1 square bracket, so we know this is a one-dimensional array. Okay. So here, if I ask for the shape of this, it will say 1 comma 12. Okay. Z is 1 row, 12 columns, and indeed it says that. And so I can call z.transpose, and this will actually transpose it. And now we'll have 12 rows and 1 column. Okay. So there you go. Right? And then the shape of z transpose is 12 comma 1. Okay. So in R, right? And I think if you're first coming from Python, if this is the first time you've seen stuff like this makes sense, okay? But in R, you could just like take a vector, throw it into a matrix, or you could even just call t on a vector and it automatically turned it into a matrix. Like calling the t function on a vector suddenly gave it a second dimension. And so so R had these little kind of quirks that were convenient to work with, but maybe logically, somebody who's unfamiliar would be surprised by that behavior, okay? Or I think this behavior with Python, I think, makes a little bit more logical sense. I don't know, maybe people would disagree, okay? But if you got a one-dimensional thing and you try to transpose it, it doesn't affect it, okay? There's no dimension to transpose. Okay, you can subset and slice much like you would slice a list, okay? So here you can say I want the object at the value at index 4, and indeed that's 4, okay? So at index 4 is basically the 5th item, okay? Something we got to always get used to. The shape is 12, and so you can again slice, okay? And 4:6 will go from, again, you have to kind of pretend that there's commas in between here, even though you can't see them anymore. And I'll go and pull out 4 and 5. Okay, with slicing there. Okay. You can, with NumPy, you can slice with a second colon, okay? And so you can say starting at 1, ending at 8 with step size 3. Okay, so this will go 1, 4, 7. All right, and if you and so you can kind of abuse this, or to get even values. Okay, And so you can say like I want the range from 0 to 100 and up through 100, but step size 2 or something like that. Okay. I mean, I guess technically. All right, and of course, this works as well too. So no, there was no really need. Maybe shortcut is not the appropriate word. Okay. All right. Okay. You can subset and slice higher dimensional arrays. Okay, and you use a comma to separate which values you want. So this is, I think we're very accustomed to this behavior in R. Okay, so here I've got a matrix or a 2-dimensional array, 3 rows, 4 columns, and here I want 1, 2. So I want row index 1, column index 2. So what value is that going to pull out? So row index 1, column index 2 is going to be 6, right? Okay. If we ask, what is this type? Okay, what is the type of this? It's just an integer. 6 is just the integer 6. Okay. Here, I can say z 0:2, 0:2. So what is 0:2 in the slice? That's going to be rows index 0 and index 1, right? And here it's going to pull out the columns index 0, index 1. So it's going to basically pull out this top corner here, 0, 1, 4, 5. Okay, so z here is going to be 0, 1, 4, 5, and that's what we get, right? And if we ask, what is this type? It's still it's still an array. Okay. Here, row index 2, all the columns. So that's going to be this bottom row, 8, 9, 10, 11. Okay. So row index 2, all columns. Okay. 8, 9, 10, 11. And when we take a look at this, okay, I mean, you can also tell you can already tell that it's one-dimensional because there's only one square bracket there. Okay, so it does kind of dimension reduction if it's able to. Okay, so it drops down. So here it's going to say it's a one-dimensional array of length 4. All right, and again here this is all rows, column index 2, which is going to be 2, 6, 10. Okay, and again it reduces down to a one-dimensional array, all right, of length 3. So now if we do this, you no longer are aware that this is a column. It's now just a one-dimensional array. Okay, when you do this, all right, this is a weird thing. Okay, when you do something like this, where you slice. When you slice an array, okay, so again here I've redefined z, and now I'm going to slice, okay, slice this to be kind of basically 0:2, 0:2, so I get 0, 1, 4, 5, okay. Slices are what we call view objects. So we saw view objects earlier with dictionaries. We had like the dictionary view objects, which are dynamically linked. And so slices are view objects. So here, if I modify this top corner to 99, this the view object gets updated as well. Okay, so z here is gets updated. You know. Obviously, I changed the first element, the 0, 0 element, to 99, and the when we subset z, okay, to the slice, it's still dynamically linked to z. Okay. So this might be surprising, okay, especially for those of us coming from R, where when we do something like this, when we've subset the array, we would expect this to be a standalone copy, okay? But in Python, they remain linked, okay? That when you've sliced it, you're creating a view object. You're basically hiding these rows and these columns when you're slicing something in Python, okay? So when I do this thing, I'm creating a new array, a range 15, and I'm reshaping it to 3, 5, and I'm calling it z. Okay, so this might be the most confusing part. Okay, so this z sub, this object is the slice of this object, right? It's this top corner of this object. When I do this, I am creating a new object, and I'm taking the name z and I'm assigning it to this, okay? So here z gets redefined, the name z gets associated with an entirely new object, and we are not actually modifying this object here. So here's the original z object, and I've modified it, but we are not modifying this. We are calling NumPy to just create a new range and reshaping that and storing that somewhere, okay? So this is not, we're not modifying anything. So we've created a new object, and the name z points to this new object, okay? And so if I ask what z looks like, okay? The top left corner of z is 0, 1, 5, 6, but z sub still points to the object formerly known as z, okay, which was not modified. And so this is going to be still the 99, 1, 4, and 5, okay? And unfortunately, because I changed name, I don't have a way to get back to this original thing. There is I could look up the ID and then reference the object at that ID. So Python, every object in Python technically gets an ID, which is basically associated with a location somewhere in memory, and you can modify that and access that. But this just creates an entirely new thing, and so the relationship between this and this is now broken, okay? But this is still pointing to a view of this object, which unfortunately I can no longer modify because I've like torn away the name associated with it, and I don't have a way to reference this by name anymore. I have to like go into the archives and find its memory ID. Okay. It's a little weird. It's a little weird. I get it. Okay. But the idea is that the view objects point to something, and if you modify that using kind of the allowable functions that modify an object in place, the view will dynamically update. Okay. But there's a difference between modifying an object in place and creating a new object and just giving it this other name, okay? So here I've created an entirely new object and just called it z. And so that dynamic link is kind of no longer there. So if you want a copy that's not going to update, you can do a copy, right? So here, here's z, the new object, which goes from 0 to 14, okay? And here I can say, all right, I want this top left corner 0, 1, 5, 6, and you do .copy, okay? And so this will create a copy, and so this is not a view object. This is not linked to this in any way, all right? So here I'm going to change the first corner to 55. The copy remains unmodified, whereas this one does. This one indeed is changed to 55. Right. So this top left corner is 55, 1, 5, and 6, and the copy remains unchanged. Okay. So this is not a view object because I used the method copy there. Is that all right? Okay. Let me talk a little bit just I guess some logistical stuff. All right, so I posted homework 1. All right, one of you have already done the whole thing and completed it and submitted it, so good job to you. Okay, the rest of you, I'm not even sure if you've downloaded the file yet, so you'll want to get started. Okay, and then I've also created a Google spreadsheet thing. Okay, and this is where you will sign up and create your groups. Okay, so I don't know. I guess you got a few minutes left, so maybe some of you already have in mind who you want in your group, and I want to have groups of 4, and I know some of you asked, like, can I have groups of 5 and stuff? I find that groups of 5, someone doesn't contribute as much as they should. Okay, so groups of 4, even then, it's still hard. Like, like groups of 1. Everyone contributes, right? But anything bigger than that, someone might carry a little bit more weight than the others. And I feel like 4 is kind of the maximum allowable something. So I really want to keep it to that. If you're having trouble, like if you don't know other people in the class, you can put down under here solo people who need teammates. The way you can fill this out is, if you got a few people, so here I created a group, just an example, okay? The red shirts, okay? You're gonna create a repository somewhere in there for your project, okay? I want the person's name, that person's GitHub account, okay? And then here I put student 2 name, and then you can also put in, like, we're looking for 2 more members or something for my group. Okay, and hopefully you guys can figure this all out. All right, and we should have about 20 groups of 4 for the class. Okay, and please just go down the line, right? Like don't like say like, oh, I like row 17, so I'm gonna just jump down there. Okay, just be a nice person and start at row 1. And work your way down, okay? If you can't figure out your group name, you can leave this TBA, but just at least get your people's names in there, okay? And I want these groups established by next Monday, and so we'll end here. And if you can take the last 2 minutes to talk to your neighbors and say, hey, do you want to be in my group, or something like that, okay? All right, we'll see you guys on Wednesday, and talk to your neighbors and find partners for your group.